Good morning, good afternoon, good evening, and good night to everyone around the globe. My name is Itai Silber. I'm from Variscite, and together with Mike Hendrick, VP Engineering, and Larry O'Connell, VP Marketing from Sequitur Labs, we are glad you joined our webinar. A comment important notice. We will share the webinar video and the presentation with each one of you via an email that we'll send on the beginning of next week. I'm sure that each one of you design your next generation project. However, I'm sure that everyone aware that in addition to have a great product, it must be safe and secure. This is our main topic of today's webinar. Larry, please go to the next slide. Thank you. So I'd like to open this presentation about Variscite. Larry, can you go again to the next slide? Thank you. 18 years ago, Variscite founders understood that many innovation companies who are expertise in their specific field, like medical, wearable, smart home, point of sales, IoT, and many more, are looking for the ARM-based, fully integrated and 100% tested platform to use for their new product and establish Variscite. In these 18 years, Variscite became to be the #1 ARM-based system on module vendor, selling over 1 million units per year. We support over 5,000 worldwide customers with thousands of proven products, which speaks for themselves. I would like to invite you to visit our website and see that we have the most diversified i.MX-based product portfolio with extensive longevity and compliance policies. Variscite is the only SOM vendor with NXP Platinum membership for the entire i.MX 8 product line. We are independent and own our state-of-the-art modern production factory. It enables stable availability and faster lead time, which now, during the worldwide shortage, become highly important. Our customers can customize their module to best fit their need and cost. Customers are not required to purchase the standard solution and pay more. We enable and assist you to customize your SOM solution to best fit your need. We are ISO 9001 and the medical 3045-85 certified and more. We provide high quality customer support, long-term longevity, and ecosystem of partners for complete end-to-end solution. We always see you, our customers, as our partner. Larry, can you go to the next slide, please? Thank you. So why better use SOM in your new product and why be our partner? Simply because it will bring you faster to the market. Do what you are expert in. Develop your innovation idea, and we will provide you a platform to make your product successful. It reduces your R&D cost as all our products are production ready, fully integrated, and proven by thousands of customers. As all our modules are 100% tested prior to shipping, you will just have to plug them into your carrier board, close the box, and ship to your customer. In case you will need to scale up for more horsepower and more features, or even construct a platform of low-end, standard, and high-end product, our products are pin-to-pin compatible with their family. I will focus and show this in a detail later. We provide high-quality documentation and free customer support, and encourage each of you to visit our product doc tab and the OS software guide detailed wiki page for each of our products. and we have up to 15 years of longevity. Larry, can you go to the next slide, please? Thank you. As promised, this slide shows our pin-to-pin compatibility. We have two main families, Varsome and Dart. Varsome uses 200-pin SO-DIMM connector, and Dart, as it named, smaller, has three 90-pin pin-to-pin connectors. Pin-to-pin compatibility allows you an easy scale-up, scale-down of your product. We have customers that build their platform and uses the single-core low-cost 6UL as their entry level, while they use the i.MX product line for mid and high-end products. Pin-to-pin reduce customer risk, as at any point of the product development cycle or product life cycle, you can easily scale up or down. You may start the development with a low-cost solution and easily scale up at any point. This may happen if your specification change or marketing wants more features, more power, or you have realized that more horsepower is needed. Pin-to-pin, of course, will make your life easier if after a few years you will decide to have a next generation product based on the current carrier board. Larry, please go to the next one. And now I'll show you a little bit about the M+. We already have the newer i.MX 8M+ that's available in both families, Dart and Varsome. So if your new product requires the new M+ processor and its additional feature, you're welcome to use it. This new M+, of course, pin-to-pin compatible within each family as showing earlier. And the main feature, as you can see, from computing perspective, it equipped with the quad A53 core and the M7 MCU for real-time tasks, the new AI machine learning accelerator that everyone waiting for. From connectivity perspective, you will get the USB 3.0, PCI Gen 3, 2 gigabit Ethernet, and you can add the pre-certified single or dual Wi-Fi and Bluetooth, plus more features that you can add. From multimedia perspective, the M+ have 2 MIPI CSI camera inputs, up to 3 displays, DSI, LVDS, HDMI, that can be used at the same time. And it has the H.265 decoder and H.264 encoder, plus more. And now I'd like to hand off the microphone to Larry O'Connell to show you how to make a great product also safe and secure. Larry, the mic is yours.
Thank you very much, Ty, and thanks everyone for having us. First, I'm going to introduce you to Sequitur Labs, then we'll go through some device security basics, and then we'll discuss methods for protecting AI at the edge, and then finally talk about our platform with Variscite and how to get it, and how to get started. Sequitur Labs' mission is to deliver chip-to-cloud security solutions for the network edge. We deliver software and cloud services to secure any smart device. Our platform is called the Sequitur Labs Security Platform, and our two products are the EmSPARK Security Suite, which is a collection of firmware tools and APIs designed to provide complete security at the device level, at the chip level, and then Empower, which is a cloud service which provides services for managing and updating devices. We compete in many markets, but some of our largest markets include industrial IoT markets like industrial automation, machine vision, building automation, the smart home, and intelligent video analytics, and we're an NXP registered partner. We're very excited about this partnership. Both companies have a mission to help you bring your products to market quickly and with less risk. As Itai pointed out, with the Variscite SOMs, you can deliver your products quickly with reduced R&D costs and deliver scalable platforms with production-ready software at high quality. Sequitur Labs also significantly reduces your risk by delivering a complete security solution, taking that steep learning curve away from you as you bring your products to market. Our chip-to-cloud security solution that we'll cover today includes secure boot, over-the-air updates, provisioning, and failure recovery, a suite of prepackaged applications for functions like cryptography, methods for protecting AI model at the edge, and robust APIs to make it easy for you to integrate our software with your product. All right, so we're in an exciting time. The IoT is true, the wave is truly upon us. We're expecting 75 billion connected devices by 2025. That's very exciting. The problem is the IoT is simply not secure. About half of firms have experienced an IoT security breach at least once. Breaches are expensive. They've been quantified as high as 10% of a product's revenue, and that does not include things like intangibles like harm to your brand and loss of your customers' trust. And this problem is only going to get more urgent as we see the exciting acceleration of AI models at the network edge. In fact, it is expected that 75% of all data will be generated at the edge, making the urgency of solving the security issues at the IoT edge more important. So with that kind of growth, why isn't the IoT secure? And the short answer is that it's very hard to do. It requires mastering a relatively complex set of features and functions required to lock down a device and manage that device. There's excellent options for silicon out there, but silicon platforms do implement security differently in hardware. And there's always pressure from customers to bring out products quickly. There's competition. As a result, often security is made a lower priority. And as a result, we have products that are not optimal for security being shipped. So how do we solve this? Well, it requires an end-to-end approach. And really what we need is a solution that will have a complete framework from end to end. That means chip to cloud for the entire product lifecycle. It should simplify security deployment and manageability. It needs to provide a trust anchor for cloud services, and it really needs to exist from the design phase all the way through the product's end of life, from when it's manufactured, deployed, and finally taken out of service. And that's our mission in life with our platform. The EmSPARK security suite attacks the secure design phase, where we deliver the entire suite of features and functions required to lock down a device, and then finally Empower delivers the cloud services required to manage, update, and protect that device when it's in the field. We've observed a 70% reduction in the security development time. Our customers can deliver products at a fraction of the cost and risk that it would take to do it on their own. And we can deliver the same product that can be delivered consistently across your Variscite platforms. On the cloud side, we provide secure updates and management. We can detect and remediate, detect threats and provide protection against those threats. And then finally, as updates and other event information comes from the silicon level, we can authenticate those messages and provide metrics to analyze the behavior of your device fleet. Let's take a quick look at the entire solution. We'll start with an IoT device, which is powered by an excellent Variscite board. And that device will be running an operating system, for example, Linux, and firmware that ultimately runs that device. The EmSPARK security suite also resides on the chip, providing the basic and advanced functions required to lock down that device, from secure boot and failure recovery to applications like key and certificate management, to advanced applications like protecting AI models at the edge. And on the cloud side, we can then register that device mutually authenticated between the device and the cloud for registration and monitoring, provide secure updates and one-time software provisioning, and then finally threat detection and remediation. Let's dive a little deeper into the EmSPARK security suite, running on a Variscite platform featuring an NXP processor. These processors feature an architecture called Trustzone, which splits the memory into two areas: a rich operating area where we run the applications, and a secure area where the security functions reside. In the rich area, we would run an operating system like Linux and the applications that control the device. The EmSPARK Security Suite APIs then provide integration into our Core T operating system. That's a trusted execution environment, a specified operating system for the secure area, and then a suite of applications that will provide the functions needed to protect the device. Cryptography, secure storage, key and certificate management, cloud integration applications like transport layer security, and also we provide an SDK so you can write your own application that can run encrypted in the secure area. This ultimately provides a suite of prepackaged features and functions, including secure boot, secure firmware updates, secure recovery in the event of a failure during boot, secure software provisioning and manufacturing, providing diversification, so every device is tied to one piece of software, anti-piracy, secure storage, and ultimately seamless integration with cloud platforms like AWS and Azure. Similarly, the Empower Cloud service is also supported consistently across NXP-enabled Variscite platforms, would provide the EmSPARK security suite with an Empower client, and ultimately delivering a complete suite of device management and insights services to manage and protect the device when it's installed in the field. Device registration featuring mutual authentication with the cloud, storage for file systems and firmware, secure over-the-air updates, one-time software provisioning and manufacturing, including diversified keys for software images, threat detection and remediation, authenticated device metrics so we can analyze the behavior of the fleet, and ultimately a high availability featuring a serverless implementation. Now I'm going to turn it over to Mike Hendrick, who's going to walk us through device security basics, starting with secure boot.
Yeah, thanks, Larry. So we're going to walk through a couple of steps here on what's going on during the secure boot process. And I'll just start out with, we start with the hardware security here at the ROM level, which is going to use the hardware features and the fuses to verify the signature of the first mutable code that it gets launched, which or gets loaded and verified, which will be the SPL. So I think if we step forward, we'll see it do that. Yep. And so the SPL has been verified. It was not encrypted. However, there is nothing in particular in the SPL that usually is sensitive from an intellectual property or anything like that. So the signature just verifies that you're running the authentic software that it should be running, and this is using the hardware to do this. The SPL, and this is where the boot process to establish the Trustzone regions, the secure memory, the non-secure memory, the shared regions, all of that's going to start to occur from the SPL. So this slide here is just pointing out that the ROM has verified this, compared the SPL, made sure that it's authentic, that it's the SPL that you've built and intended to run on this particular piece of hardware, and it won't run, and because it's in secure mode, it won't run any other SPL unless it's signed correctly. So I think step forward and we'll talk about what the SPL is going to actually do here. Yeah, so the SPL is going to be verifying the memory, or not verifying, but isolating the memory to the secure, the non-secure regions, as I mentioned, so that you basically have the secure enclave or the secure environment and the non-secure environment, and establishing where those are defined, and that is hardware enforced separation, which is what the Trustzone architecture provides, is that hardware enforcement of these isolation or of these regions. Once you have them separated, our trusted execution environment is loaded to the secure region and initiated. It is, at this point, you're not just verifying signatures, you're actually decrypting the payloads. So Core T and everything that's there and everything that you see following from this point are actually encrypted payloads when they're sitting in the non-volatile memory. And not only are they encrypted, they're diversified. So every device has different encryption keys for those payloads. So that if you were to take these images and put them onto another device, exactly the same, an exact duplicate of this device that was manufactured maybe at the same time, these payloads will not run on that other device because the keys that are encrypting these boot payloads are different. And so they wouldn't run on a separate device. So at this stage, you've essentially initiated the secure OS, and you can see the picture here, architecture, and then we're going to step forward. And the next step will be basically to load the rich OS. And this is a very simplified explanation of what's going on in the boot process. I mean, if you've worked in embedded systems or you've worked with Linux, you know that you have the device tree and you have a bunch of things going on there in that rich OS. In this particular case, we're using the SPL and U-boot combination. So U-boot's actually running non-secure as part of the initiation of the rich OS. But all of the components are being loaded and verified and decrypted from that secure side by the SPL. You can see here in the architecture that you've got the two separate regions of memory. You've got the shared memory, which the two sides use to talk to each other. And then you have the Linux OS and loaded to the non-secure side. So I think step forward. They get lost sometimes in all the stepping through all the animations. So once you have Linux up and running, Linux is going to go and do what Linux does, which is mount a file system and start loading those applications. So you'll go through the initialization of Linux. It'll load file systems at that point. So at that point you're essentially into a normal Linux boot sequence. Now, what you can do to harden that even is you can use keys that came out of the core T that were supplied up through U-boot to Linux to do things like de-encrypt and de-verity to verify your file systems and to make sure those are encrypted when they're at rest and protect everything that's in that rich OS as well, where those keys are protected by the secure side before they're passed over to Linux to be used at rest. So this is, I think we have a summary slide. So if you want to step, yeah. So essentially you've got diversified keys, you've verified each stage of the boot process. So you know that you have authentic payloads, you know that you've established your secure and non-secure regions in the system, and you've basically have the secure side where you can access all of your keys and certificates that Larry was talking about in the overall picture, and you have your rich OS up and running your application. You also, like I said, those are unique keys per device. You also have device IDs that were created during the initial provisioning that'll be unique to the device that you will be able to access to use to identify the device, and those are all tied back to the hardware root of trust all the way back at the ROM, which load the SPL, and then the SPL was able to extract those and make them available as the system comes up. And also on this product with the NXP hardware and the Variscite boards, there are various registers and stuff that you set through this process to advance the boot stage, so that keys that are used to decrypt some of the components in these early boot stages, as you advance those registers past those boot stages, those keys become unavailable until you go through a reset of the chip. So the only way to get back to some of those components is to go all the way back to a reset and start the verification process over again, so that you're always booting known good software to do that. And that will come up again. That little view will come up again in the OTA section. But that is like I said, a sort of a high-level view of a secure encrypted boot process with diversified keys that is establishing the trust zone and verifying all of the components and bringing them up in a secure, protected fashion there. So let's step forward. Yeah, so as I mentioned, the secure firmware updates. Once you've established such a strong secure boot process, the secure update firmware update comes into play. And the reason that the update is one of the ways can be a high risk of compromise if you allow firmware updates to be done. So you want to make sure that your firmware is authenticated from a trusted source. You want to make sure that it is intended for the device, and you because it will be replacing the firmware or components of the firmware that you currently have on the device. And so so you can see here there are several things that that happen. One is we use signatures PKI to basically verify the authenticity of the firmware that will be applied, and we do it a couple of times. So one, you can do the firmware, you can do that authenticity check right when you receive it, just to verify that nothing happened in transit. Because not only does it verify against malicious attack, it also verifies against just like a noisy data channel or something that may have corrupted the file unintentionally. So the very first thing you do is you can authenticate the firmware, and that will verify that you have a payload that can be applied. And then you will initiate basically the update process. There are a couple of things on here that are mentioned, like depending on, we know that there are business needs for around rollback prevention, and that sometimes you do want to prevent rollback. Sometimes you have to maintain a window of acceptable rollbacks that you can make use of. So we've worked with customers who do both, where they have a window of rollbacks, where they have very specific firmwares that especially if there's a high security issue, you may not want to allow rollback to that version. And so using using a window, you can allow firmware updates only to certain versions and above. We provide, because each chip is diversified and has a unique set of keys that is only accessible in that early boot stage. We provide the mechanism in the boot to recognize that there is a firmware available and apply that firmware when those keys are available, because the firmware payload that will come down is encrypted and signed, but it's available for all the devices in your field. And then when it gets applied to a specific device, it needs to be verified, decrypted, and re-encrypted with the diversified keys that are specifically on that device for that boot process. And those diversified keys were generated during the initial provisioning and never exported, so they aren't available anywhere except for on the device. So you send a generically encrypted payload, and with the NXP devices, they provide a very nice feature called manufacturing protection, which allow us to generate that generically encrypted payload that can only be decrypted on an actual NXP device of the same type, and signed with the fuse pattern that is used to verify the SPL. All that has to match in order for it to decrypt the generic payload. And then it can use, once it has that decrypted, it can re-encrypt it and apply it as the update with the device specific keys. So you've turned that generic payload, you've verified it, you've been able to recognize it, make sure that it fits the parameters of can this be applied or not based on the versioning, and then you're able to re-encrypt it and put it onto the device for future boots. And this also, the other big impact here, I think if we step forward one slide, is going to be around resiliency. So one of the things that can happen is if the boot fails to complete the process, so you get the first stage ROM and the second stage boot later, but you're either applying an update or you've applied an update that maybe had an error in it that because of whatever slipped past QA, it may not boot. You may have something else has just gone wrong over time, and the bootloader actually has a secondary failover so that it can boot an alternative system. And that can either be a completely redundant system, or it could be a recovery system. That really depends on sort of your business needs and what you would like to do there. But you have a completely secondary a boot path there that will come up in the event that the primary doesn't boot. And we provide this with a number of parameters that you can set. One of the things it does is it uses the hardware watchdog on the device to monitor for the completion of the boot stage all the way up to the application level. So if that fails, that will trigger the reset. We're able to observe that the reset was due to the watchdog. And we don't necessarily just fail over on the first one, because that may lead to, well, you could end up in a failover situation. Say you had a brownout or something in the middle of a boot sequence, you'd fail over immediately. But what we do is instead we keep we have a counter that you set sort of based on your observations in your device as to how many failed attempts before it would fail over to the secondary system. And obviously, if something's wrong, it's going to continue to fail on that primary boot path. So after 4, I think our default is 5 times. It will fail over to the secondary one, but that's adjustable depending on the situation you're in. You can adjust that counter. And then every time you successfully boot, you reset that counter so that you're coming up through a successful boot. And then this also provides, with this failure recovery, it also provides a mechanism when you apply an update. You can control which of the 2 paths you're updating and which one's going to be primary. So you can always update the secondary and then switch to the secondary and make it the primary during an update. So all of this works hand in hand, and we've spent some time discussing the boot path, the OTA, and this failure recovery. They're all very linked, because getting the security established on the device with the diversified keys and being able to account for when you need to apply an update, all of those are interlinked and part of the same in the same region of the device, as far as the sequencing of when those things need to occur and when they need access to certain keys that will be locked away are disabled until resets come through. So we've had to account for all of these types of options and all of these components in the boot sequencing, so that we have a complete solution that's not just turning on security for you, but actually allowing you to build a product that is resilient, can be updated, and has the secure boot all there. So from that, let's move forward. So the last piece is the secure provisioning, and this is essentially so we talked a lot about the update and how it needed to be secured and encrypted. The secure provisioning essentially is a very similar thing for the manufacturing process, because the last thing we want to do is enable all the security and then send it off to a contract manufacturer where your IP is completely exposed during that process. So we provide, I think we have some images if we want to step forward. Yeah, so we provide some, we provide tools that create provisioning images that will go onto a pristine device in your manufacturer and configure the device, set those initial sets of fuses and hardware, load up a provisioning bootloader, which will verify that those fuses are set, and then be able to decrypt, similar to the process that the OTA did, the provisioning payloads on the device, and then create those device-specific keys on those diversified keys on each device, and re-encrypt the provisioning payload at that point. The other thing it does is it creates the unique device ID at this point. This is all using the TRNG of the device, the true random number generator. So you're getting good solid keys there, and you're sending encrypted signed key payloads that are only runnable on a device that has been has the fuses set to your set of authentication keys. So you have control of the IP that's in those, that's going to be provisioned to your device. So that's tied very much to that. So I think now we're going to talk a little bit about chip to cloud. So so the EmSPARK includes the components to enable chip to cloud. As Larry showed, it has a TLS stack which does mutual authentication, where the CA and, for your server side and the device identity keys are all managed in the trusted side, so that you can basically register to a service and use mutual authentication with all of the keys and credentials being protected in the secure side, and then you can collect tamper events and like boot events, and why is the device booting? Are there tamper events going on? And you can collect all that information and report it up, and all of that information can be signed so that you can verify the authenticity of that coming into your backend. So you have a solid chain of custody of any of those kinds of events and create a good audit trail. So let's step forward. And so, yep. So now we're going to talk about EmPower. The previous slide, the chip to cloud stuff, it can be implemented from EmSPARK, but with EmPower, we provide a service where we've done the integration, we provide a client, and we provide a backend so that you don't have to develop those components yourself. So much like, so it's going to be a little bit of the mutual authentication example that I just mentioned. So basically, you're going to send the device certificate with you that's using the device private, or using the device key pair, where the private key has never left the device since that initial provisioning step that we talked about a minute ago. It's been buried in the trusted side and never has left there. However, the public key and the certificate will be sent up to the server, and it can be recognized because the signature on that certificate was defined as a certificate that EmPower can recognize during a provisioning step. So the server will receive it, recognizing that certificate authority as something that it recognizes, sends it a challenge in its own certificate back, and step forward one more. And then the device checks the certificate of the server, verifies that it's routed to a CA that's managed on the trusted side, and then signs that challenge with its private key and sends it back, and a session is now established. So we now know that a device that has never been seen by EmPower has been authenticated and registered to the system as an authentic device that was configured correctly to talk to EmPower with the correct CAs assigned to it. So I think we can step forward. Yep. And so once you have that session established, now, as I was mentioning a minute ago, we can use that client to report regular status and get information back from EmPower. So let's see the first communication. So basically, the device is going to send status messages to the server, and those are both periodic and event driven, so that they can basically report its version, report tamper events, report its current status. Basically, the cloud will evaluate the status and respond appropriately. So most of the time it'll respond okay, just receive the status. Sometimes you'll have updates available, and it'll provide back a response saying, hey, there's an update. And then that update message will come back to the device. The device will process it, and recognize that update message that was sent back was actually a signed command. So it's even before it even goes to get the update, it has to verify that the update, that the command requesting the update was a valid command coming from signed correctly. So we've established a secure session with the cloud, and we also verify each command that is sent down to the device to verify that it's an authentic command, not just trusting the channel blindly, but also trusting each of those. So it will receive the details of where that update is. It will retrieve that update and perform the update per the process we talked about earlier, because once it has the update, that's just the normal EmSPARK update that we talked about earlier. Those updates are not just the firmware, but you can also send down arbitrary binaries to update the application. You can update the entire file system, so things that are even not just the firmware, but some of those other components. And then once it's done, it'll send its status up to the cloud in case you have a chain of updates or anything like that you may want to perform, version 1 to 2. So if a new device comes on, it's version 1 and there's a version 3, but it has to go through 2. You can go 1, 2, and then it'll send it'll say it's up to 2. The cloud will respond and say, hey, you have 3 now, and it can go through that whole sequence and get current. Otherwise, it'll just get the okay back to let it know everything is done. One note there is that the Empower side is not trying to keep track of what the devices are on. It always takes what the device says its status is, and it holds that so you can see on the cloud side what everything is currently reporting, but it doesn't rely on that to automatically tell devices that they have updates. It's going to wait for the device to give its current status, and always use that as the information of record is what the device is reporting. So anyway, so I think we can step forward. I think. Okay, so finally, we're going to talk a little bit about protecting IP, specifically AI models at the edge. AI models present a particularly challenging thing to protect. So we'll talk about that. So we want to ensure that the model is authentic, and we want to hide the model from attackers. It's very high, typically very high intellectual property value, and it also is usually performing pretty critical tasks. So you want to make sure that both of those things are true, that it's authentic and it's protected. So the simplest way is to use the SDK. I think Larry had this in the first picture. So if you want to just step forward and show that the trusted application is going to decrypt and load. So on disk, it's going to be encrypted in an application or whatever you're running. It's going to load that and pass it over to the secure side where it can decrypt that encrypted payload and then load it directly back into memory. Is there another? Yeah, load it directly back into memory. And so as it's a running application, it is now running in memory. But on the disk or on flash or non-volatile, it is an encrypted application. It only exists in clear text and in memory, and so that provides some level of protection for applications, especially things like AI and models that may be more at risk. So let's talk about some other methods. Yeah, so that the previous slide was just we had a couple of details about the specifics of how our product and some of the things you would see in the API, which if you look at we'll talk about some evaluation kits and you can see some of those specifics. A more higher level of protection is to, much like we've separated secure and non-secure, we can isolate the Linux applications, and this is particularly helpful in hardware where like the 8M Plus, where you have dedicated hardware to run those models. So here we're going to use a hypervisor that actually segments the hardware, segments cores, and runs 2 instances of Linux, not virtualized on top of on virtualized CPUs, but actually on dedicated hardware. And so what we'll see here is that the 2 Linuxes can talk to each other through an IP connection. The isolated Linux is really for running your business logic UI, applications that tend to have a higher attack surface. And so we keep it isolated from the place that's going to have access directly to the model and to the hardware that's running the model. And that's the idea with this one. So if we want to step forward, we have a couple slides to talk about this. Yeah, there we go. So a typical application, so this is a pretty big machine here that would have, like, say, 8 cores. You're running everything. You're running your Linux OS. You're running all your business logic, your UI. Everything is running in a single space. You have your video. In this case, is a video model that would be taking that image feed and doing inferences on that image. video. And this is a sort of a typical, everything's run in one big flat space, and a compromise of Linux gives you access to everything, compromising data, changing the data, doing all that, and even where it's running on dedicated hardware there, the cores all have access to that. So it's a very, you can corrupt and steal the model basically at this point. So what the hypervisor model does, you want to step forward? Go ahead and step, yeah. So what we've done in the hypervisor model is we've isolated the sort of what we call the client, which is the higher risk instance, and it has the applications that may present a higher attack surface. What we've done the server side is a very locked down, very isolated, very limited Linux that's really meant just to run the model and interact with the hardware. It can also interact with Trustzone, so that becomes available as well. But by limiting this, you reduce the attack surface. And the reason that you do this over just purely doing it through Trustzone is a lot of the AI inference models that work with hardware have a fairly large software stack, and so porting that out of Linux into other environments, especially with something like the T, become a bit of a challenge to bring all that software over. And bringing all that software over would also introduce attack surfaces inside of the T. So we keep it isolated to Linux. We isolate it from a lot of the other software that's being written and a lot of the stuff that is touched more frequently, and sort of have this defense in depth, multiple layers, so that one compromise doesn't compromise the whole system. You keep things isolated and limited by doing this. And once again, this hypervisor is not virtualizing cores or CPUs. It's using hardware isolation of these cores and CPUs. So you're running, a few of the cores are running one thing, and a number of other cores are running the isolated, the limited Linux instance. And the number of cores that would be on either side is really depends on the performance you need, and that would need to be tuned in a specific application. So I think that's the last slide, Larry, maybe. I think there's one more I might have.
Yep, that's it. So I'll take it,
Thanks.
and we will talk about how to actually make it happen with the EmSPARK security suite and the board. Thanks, Mike, for the technical overview. And let's talk now about how you can work with Variscite and Sequitur to get started. Variscite will provide the best-in-class SOM platforms that we saw earlier today, and we support those two, the VAR-SOM i.MX Plus and the Dart-SOM i.MX Plus. And Sequitur Labs provides, in support of Variscite, the EmSPARK security suite, the Empower Cloud services. We also provide engineering services. We can help you with customization, implementation, and finally, support. So to get started, choose your Variscite evaluation board that Ete reviewed earlier in this webinar. Then go ahead and head to the Variscite site. That's EmSPARK for Variscite, sequiturlabs.com, EmSPARK for Variscite. You can also navigate there through the product page. On that Variscite page, you can scroll down to the documentation. You'll see the Getting Started guide, a guide for doing secure boot updates and provisioning, and then the user guide, which will show you how to use our APIs and applications to do the rest of the functions that Mike described today. From here, you can also go ahead and download the eval kit. Just click through inside the beta agreement and then download the software. Then you go ahead and install your kit using the Getting Started guide. We also have a video on the same site that will walk you through step-by-step exactly how to do it. That goes through the very first piece of laying out the equipment all the way through the secure boot and provisioning process. And that concludes the webinar today. And now we'll go ahead and take your questions. And we'll go ahead and go through the questions that have been answered through the course of the webinar. Feel free to go ahead and enter the ones that you are interested in. The first one, and this one will be for Mike. EmSPARK, does it provide anomaly-based intrusion detection or signature-based?
The intrusion detection that we typically provide is based on the hardware features. So we're looking at the environmentals. We're looking at, yeah. So it's mostly the hardware-based tamper events that we're looking at. And then the other thing that we can report up is going to be like boot status states and things like that. Those are the other things. The triggers for the local remediation is going to be those tamper security events that are the hardware based. So.
Okay, thanks, Mike. Another one for you. Can EmSPARK protect against insider attacks? What is done for protecting against insider threats?
So we worked with customers in the past on defining their internal sort of insider threats, and part of that comes down to so we provide development and production kits for building final images and things like that, and the fact that the way they produce those provisioning images, you can isolate who has access to those keys. However, if there is somebody who has that level of trust in the organization, they would have, you can create isolation much like we do in the system. So you can have people who have access to the production system and producing the production keys, producing those provisioning and production images. You can also have access to maybe the development systems and some of that sensitive IP that you submit into the repos, but we can't provide 100% because people have access to that code, and depending on what kind of insider threat specifically, we could help map that out and show what pieces they would need access to in order to alleviate or to minimize the risk of the particular threat that you would actually you'd be defining in your system. Like I said, we've done that with customers where they very much had insider threat scenarios in their threat models, and so we talked about where they put specific systems that would produce like the encrypted payloads for provisioning versus the development systems and who had access and things like that.
Okay, great. Okay, cloud-based servers are mostly virtual machines or containers. So is EmSPARK launched on the host and does it provide an introspection of VMs, or is it running within the virtualized operating system?
EmSPARK is a hosted backend. I'm not sure I fully understand that question. It doesn't do anything. EmSPARK doesn't do anything to inspect that side. It's just collecting the events and providing the connectivity and collecting events from a fleet of devices to do analysis of the entire fleet to see if there's systematic problems. That's what it's sort of doing for the tamper side. Yeah.
Okay. We can come back to that one. We'll send an email out on that one.
Yeah.
Okay, great. Okay, how are images for the Cortex-M handled during the secure boot process?
So during the boot process, during that SPL, you can actually specify a region that the M is going to be. Is it going to be secure or non-secure? So you have to specify where it's going to live on as a domain master, and then you just much like you load the Linux from the non-volatile, you decrypt and load the Linux image, and the Core T image, you would load an M3 to the specified region where the M4 was going to use to boot from, and handle it there. Okay,
great. In Linux OS, AppArmor.
Sorry, real quick. We do have customers who have used the Cortex-M on the NXP and do exactly what maybe wasn't a great explanation, but we have customers who are actually doing that and using that process. And if you want to get into specifics, we'd be happy to have that exact discussion. But it's very easy to have it load up there. So.
Okay, great. Okay, just a couple more questions. We are running out of time, but we will certainly get back to all of you with the questions you posted. Which is the Linux update agent used for secure over-the-air updates?
So on the Linux side, On the firmware side, it is all EmSPARK. So everything that's updating from the basically Linux kernel down, it's that EmSPARK component. So if it's Core T, U-boot, DTB, even the SPL, all of that is part of the EmSPARK software to update those. And there's a description in the secure boot and provisioning, I think, that discusses that. And then for the Linux side, we provide either binary updates and or complete files. So a complete file system update would just be a replace your file system, but the agent, if you had a specific update tool that you wanted to use, that you'd be free to use that, and you could use the EmSPARK and the Empower APIs to retrieve your binaries that would be used in that process. We are not working directly with any other agents to update the Linux side. We leave that more to your implementation. We provide the mechanism to get the updates to the device and encrypted and decrypted and verified, and then you can apply them in the Linux system as need be.
Okay, and we're at the top of the hour, so unfortunately that's all the questions we can go through. We will get back to you on the rest of them. And with that, I'd like to thank everyone for joining this webinar, and we look forward to working with you on this great solution with Variscite and Sequitur in the future.
Yes, thank you, Larry, and thank you, Mike. And maybe if you go to the next slide, everyone can see that our contact, we have actually 2 slides left, the website of, and us. So thank you, everyone, to join us. And thank you, Larry. And please send us an email if you have further questions, and we will be happy to answer you. And have a great day.